Happy to see so relatively large number of you, despite the nice weather outside, and I know also it's an application deadline for two major programs today, so people are perhaps very busy. Anyway, I want to introduce Professor Kevin Webb from the University, Purdue University at Illinois. He is sort of a hybrid between Australia and the United States, meaning that he was brought up and raised in Australia, but he has had most of his career in the US. And he had his PhD at the University of Illinois at Urbana. It's quite close by, Indiana. Well, it's a neighboring state. In 1984. So, but in between he has moved around quite a lot, especially in his research directions. But I think one can say that optics and photonics are major themes in his interest. The last few years he has been particularly interested in something called negative index materials, which is a very fascinating and very applicable area. That means optical indices which are negative refraction. And he's also interested in waveguides and waveguides at very small scales, nanoscales. And I should say thirdly also imaging in general, and I think his talk today will concern mostly about imaging and its connection to biological or medical applications. And he is now also, he has a sabbatical 1 year, so he spends that sabbatical partly at our lab, Theoretical Chemistry, School of Biotechnology, and partly also at Kista Photonics, collaborating with Professor Lars Tulenda. So, I think the word is yours now.
Thanks, Hans. My accent is also a hybrid. How's the volume? Is it okay? So, I'd like to talk about medical imaging with light, and meaning ultimately there may be some sort of clinical applications of what I'm going to talk about, but we haven't been pursuing those directly. We've been looking at some fundamental issues that I'd like to talk about, and perhaps some of them might be ultimately useful in some sort of clinical setting. And I'd like to break the discussion into two related topics. The first one is about speckle. It's basically coherent statistical optics. And the second one is tomography using a forward model for scatter, which is the diffusion equation. So it treats photons like particles, billiard balls, and some results we have related to that. And the two topics are related in the sense of that some information that one can get out of statistical optics or speckle type measurements one can use in reconstructing images based on a diffusion equation. So that's the overlap. And I'd like to entertain questions, if it's okay, as we go, because I can modify the presentation on the fly and really learn something from your questions as we go, perhaps. So, if I shine this laser on the wall, then you see some speckle, and that's the granularity. And that granularity gives us some information. First of all, it's a function of the coherence of the light. The broader the bandwidth of the light, the less coherent it is, the less granularity we see. But given the coherence length of the laser, the granularity that we see, looking at the speckle spot, if I can hold it still enough, looking at the laser spot rather, we see some granularity, some speckles that have bright and dark regions that are characteristic of the wall. And so if we knew something about the laser, we could learn something about the wall by looking at the laser scattered light or the speckle pattern. So that's sort of qualitatively how we might understand something about the wall as the scattering medium. So the tissue also has scattering properties that in the red and near infrared involve mostly scatter and less absorption. So the light comes out but is scattered a lot. And if the light were coherent enough, if I shone this laser through my hand and I had a sensitive detector on the other side, then I would could measure a speckle pattern as a function of space. And by doing the right kind of measurement, I could potentially learn something about the tissue properties in my hand. And that's what this figure is about. So here's a speckle pattern. This is measured with quite coherent light, 5 megahertz bandwidth. This happens to be 850 nanometer light. And this is what the camera image would show. So when we look at this image with a camera, then we need to have these spots reasonably large compared to the pixel size on the camera so we can resolve each of them. And enough spots in here so that we can generate statistics from one image, let's say, without moving the image spot around. And so this turns out to be about a millimeter by millimeter. And if we look at the statistics here, then we can generate, this is intensity, we can generate a mean and a standard deviation. And if we take a ratio of the standard deviation to the mean, then that's a measure of contrast. And so if the contrast were 1, then that would be the case with perfectly coherent light. And as I increase the bandwidth of the light, this is a case here where it's 17 gigahertz, so you notice it's a little more washed out, then the contrast reduces. So we have less granularity with increasing bandwidth of light. But if we look at these different curves, then the more scatter we have, the less the contrast. In other words, if I fix the coherence of the light and I increase the amount of scatter, then this curve drops down. I have less granularity. So I have a measure then, let's forget about loss at this stage, I have a measure of the amount of scatter from the contrast ratio. Measure that. So that tells me that I can learn something about the scattering properties of whatever I'm looking at, let's say it's tissue, okay, from a simple contrast ratio measurement, where perhaps I have control over the bandwidth of light, or I have fixed bandwidth light, but it's at the appropriate coherence length or bandwidth. So one way to do this kind of measurement is to take a tunable laser diode. And what this really is the laser diode with an external cavity, and that external cavity length can be tuned, and allows you to tune the line of the laser over some bandwidth. And this particular laser allows us to tune over about 80 gigahertz. And if we stare at the light coming out during the period that we scan the laser, then what we effectively do is synthesize a particular bandwidth for the light, or a particular coherence length. So that's one way this measurement can be made. And this aperture here, this is imaging optics, and we could do a little more sophisticated way, but this aperture is what dictates the size of the speckle. And the image plane is over here where the camera is. And this is a scattering medium, and the results that I showed in the previous slide and the next few figures relate to, it's basically titanium dioxide scatterers about 50 nanometer diameter in a clear acrylic background. And at this wavelength, it's white plastic basically. Let me mention one other thing here too. This, another way to look at this scattering medium is, this is a frequency domain picture, and we talked about speckle, which is a spatial description, so we're looking at a very small spot on the back side of the scattering medium. Light comes in, scatters, and we look at this image as a spot here, projected onto the camera, and that's the speckle image. And another way to look at the problem is in the temporal domain. If I can put in an impulse of light, so this is the time axis here, into this scattering medium, then I can think about, at least conceptually, a path length distribution for these photons. And if I measure the light that comes out at one point on the output surface there, as a function of time, then it might look something like this. So the impulse is being smeared out, and the width of this is governed by the amount of scatter. So in other words, if I were able to measure this impulse response, then given the position of the source and the position of my detector, then I would understand something about the scattering properties of the sample. So this impulse response, or as we'll see, and this can be a path length distribution, or using velocity I can convert it into a temporal distribution. And if I normalize that, I can consider it as a density function. So here's a situation where now we have white plastic, and we have something in the middle here that could have more scatter or less scatter, or some different scattering properties. Light comes in from the back, and we measure an image from the front and onto the camera. And this shows contrast ratio difference. So we take the, without the inhomogeneity, in other words with solid background material, we measure a speckle image. We can get the statistics of that. We put in the scatter, we measure the speckle image. We can get the statistics, namely the contrast ratio, and we can form a difference. And these figures give that difference. And this is the case when it's a void, 5 megahertz bandwidth light, 17 gigahertz bandwidth light, and more dense meaning more scattering. And the sign of the contrast, this is positive and negative, gives us, I think, gives us information about the scattering properties. Here, the central region is less scattering, here it's more scattering. It also tells us that if we don't have the right sort of bandwidth, we really don't get sensitivity to that. And going back to the temporal response, what it's really saying is that we need, if we look at the Fourier transform of this impulse response, we need to capture an adequate amount of that spectrum to really learn something about the scattering properties. And that's why the 17 gigahertz result works quite well and the 5 megahertz doesn't. But that's only loosely an image. What we're really showing is sensitivity to some inhomogeneity. And again, we're ultimately thinking that the plastic may be something more clinically relevant. So, this temporal distribution, or the temporal impulse response, we can think about it. If I have a source here and a detector over here, then I can think about it as a Green's function solution for a particular forward model, if I have a model that's appropriate. So, one possible model in a regime where there is adequate scatter, and the scatterers obey certain properties, then the diffusion equation becomes a satisfactory model. And this shows a set of temporal impulse responses for a diffusion model with different amounts of scatter. And this is D is the thickness of the slab, and as the slab thickness increases, then this temporal duration increases. And as the amount of scatter increases, then that also increases. And this, one use of S primed to get an idea, if we can neglect absorption, then the transport mean free path is 1 on this number. And so if I take 1 on 10 centimetre, inverse centimetres for instance, then I get 1 millimetre. And that property is something like we might expect from tissue. In other words, if I send photons into tissue, then after about 1 millimetre, I lose memory of the incident photon direction. And so it's not the distance between scatterers, it's the length that the photon needs to travel for its direction to become randomized. And so this kind of scattering, it's called a reduced scattering coefficient, is representative of tissue. And for the diffusion equation to be reasonable, then we would need some number of these lengths, maybe an order of magnitude more, maybe 10 times the mean free path to be reasonable, and the model wouldn't work in boundaries, of course. Anyway, but this is a way one can generate then a model representation for the temporal impulse response. And this is the diffusion equation that it comes from. And here phi is a power density, a photon density, so it has units of power per unit area as a function of position and time, or we take a Fourier transform of this, and I'll do that later. So it's a function of frequency, where that is the modulation frequency. So, and this is the diffusion coefficient here, which is a function of this reduced scattering coefficient and the absorption. And basically 3 times D is 1 on u sub S primed if this guy is 0, and that's the transport length, or length for randomization. So what the detector sees is related to the gradient of this quantity phi. And if n hat is a direction normal to the detector, then the amount of power that the detector measures is then given by this quantity. And so then we can construct a normalized temporal impulse response, P as a function of R and T. And that's what we could plot and think of as then basically a density function that gives a path length or a temporal distribution for the photons. So that'll come up a few times. And the source here, this is the source for the photons. The idea is that if I send light into the scattering medium, one model suggests that I could consider the excitation as a point source some distance inside the scattering medium. And that's why this is the Dirac delta function. So, if we have a lot of scatter and I send light in with one particular polarization, then the results I showed before, what we want to look at is the polarized speckle pattern. So we look at the light that comes out of the scattering medium with the particular polarization, for example, the incident. I'm pointing in a particular direction because I'm implying linear, but it doesn't have to be. If I measure the cross-pole light and I have enough scatter, I get the same information. In other words, the light becomes completely depolarized. If I have less scatter, or I have some organized anisotropy in the scatter, then I don't get the same information. And this sort of raises an issue of an interesting regime where we have less scatter and we send light in with one particular polarization and we look at both the co-polarized light and the cross-polarized light, and the idea that there may be information in these different measurements. And basically the idea is that if I send light in with one polarization, and here's, for example, using linear as the copole, the cross-pole, and if I think about what happens in time, and if I send in an impulse of light, then the temporal responses for these two polarization states may differ. And those differences may then lead to some understanding about the scattering properties. So if we look at a measurement, and this is a less scattering material, this shows the mean intensity as a function of thickness in the various polarization states for linear and circular, the copole and the cross-pole. And here's another measure as the degree of polarization as a function of sample thickness. What's interesting here is that linear and circular polarization responses are not the same. And we can understand these differences based on a single scattering model, Lee scattering type. And this shows some measurements, degree of polarization, and temporal impulse responses for co- and cross-polarized light. One interesting thing that comes up then is if in this sort of intermediate regime, what kind of model might be appropriate to try to apply, because it's too complicated. There are too many unknowns to solve Maxwell's equation, to solve a wave equation for this problem. So when there's a lot of scatter, we can think about a diffusion kind of model. And for lesser amounts of scatter, perhaps we're in a regime where we might apply a Boltzmann transport equation model with polarization information. So I showed a laser setup where we had control over the frequency of the laser. We could scan the laser frequency. So we can then write the random variable intensity at some particular frequency, and the superscript represents polarization. And we can adjust the frequency. So I can think about a speckle pattern at frequency nu0 and nu0 plus delta nu, where delta nu1 rather is the frequency offset. And we can define normalized intensities by subtracting the mean and dividing by the mean. And if we take a second order intensity correlation of two different speckle patterns, and this is the average over space, if you like, but really it's a statistical average. Then using the normalized, which is the tilde on top quantities, then this correlation is equal to the magnitude squared of, this guy is the Fourier transform of the temporal impulse response. So that P of t from earlier, the Fourier transform of that is P of delta nu. So in other words, this second order correlation of intensity with frequency gives us access to the magnitude of the Fourier transform of the temporal impulse response. And this relies on the idea that the statistics are circular Gaussian, and there's a moment theorem that was derived by Reed a long time ago that says if the fields are circular Gaussian, if we assume that, then we can write this result. A circular Gaussian means if I have complex fields, I look in the complex domain, I have real and imaginary, then I have circularity of the field statistics. And so I can separate out the magnitude and the phase terms and treat them separately, and that's how we can write that result. So here's the tunable laser diode again, polarizer, here's the white plastic, the scattering medium, the imaging optics, here's a speckle pattern. As we adjust the laser frequency, then the speckle pattern changes. And so we can measure these patterns as frequency is changed, and we can determine the second order correlation as a function of frequency. And this shows how the decorrelation occurs. And if we have more scatter, then the decorrelation, meaning a thicker sample, happens more rapidly with frequency. And this shows a comparison of the experiment with the diffusion model. And in this case, the diffusion model works reasonably well because there's a lot of scatter. And the diffusion model, again, what it really represents is shine light through this. You have a speckle pattern. It doesn't, of course, capture all that. You need the wave effects, but it captures the average. It's a function of this frequency variable, which is the Fourier transform variable corresponding to time in the diffusion equation model. Yep. So if we look at this kind of measurement for different polarization states, then we see that the decorrelation is a function of the polarization state for lesser scatter. So if we have this shows the copole for linear and circular, and the cross pole for linear and circular for a particular case. And notice again that the linear and circular are not the same. And this temporal, this spectral information rather, is also a measure of the temporal duration of those impulse responses. So what's interesting, what we found out is that if you take, instead of 2, you take 3 speckle patterns, just intensity, and you do a correlation involving 2 offset frequencies, then it turns out that you have enough information to reconstruct the temporal impulse response directly. So what I said is that initially was that the second order correlation, meaning intensity at one frequency correlated with intensity at another frequency, gives us the magnitude of the Fourier transform of the temporal impulse response. But we don't have phase information. It turns out if you use 3 frequencies, you get access to the Fourier phase information by something called the bispectral transform. And which is quite interesting, because what that means is that you can just measure intensity and you can get phase information out of that. And that comes about, here's the bispectrum, which is related to a third order correlation with 2 time variables. And so the third order correlation is related to this quantity, and this is the Fourier transform of this guy. So that's how we get access to the Fourier phase, basically. So anyway, so then if we make both these types of measurements, then we can get directly the temporal impulse response up to a conjugate variable. We don't know which way it's heading in time, but usually that's not a problem. Another interesting thing is that we can put this into a scattering sample into an interferometer, So here's the source again. Light comes down. This just measures frequency, so we know what frequency the laser is at. And here's an interferometer where this scattering sample is in one arm, and this is the reference arm, and here's our detector. And now it's a point detector. It's a very small detector, very small relative to the speckle size. So what we do here is we scan the laser frequency and measure over some time. So we measure the light coming out of this detector. And what's interesting is that if we Fourier transform that result, then we get, this is like the current coming out of the photodiode detector, then we get this kind of information. And if we window out this, shift it back to 0, then this corresponds to the temporal information that we want. So it's rather interesting. And this is really what's called spectral interferometry, but as opposed to applied to a random medium. And if we Fourier transform that and look at the statistics, we can get access directly. Excuse me, we Fourier transform that, and we get access directly to the field. So this interferometer is really just a way to measure field directly at optical frequencies. So if we just stare at it with a camera, of course, we just get intensity. But if we make an interferometer measurement and do this kind of simple signal processing, we can get access directly to the field. So we can measure the field statistics. What's interesting is, and rather surprising, is we're able to show for the first time that for these kinds of materials that the fields are actually circular Gaussian over a large set of parameter ranges. And all of statistical optics is based on the assumption that the fields are Gaussian. And it also leads to the concept of speckle in time. In other words, we take the magnitude of the field squared as a function of time we would get. Then what we're really looking at here as we scan the frequency is we're looking at how some region within a given speckle spot, how the intensity changes over time, and we get these kinds of results. So we can think about speckle in time and speckle in space. And if we average all of these guys, then we get the ensemble average temporal impulse response. And one final slide I wanted to show related to statistical optics is that it turns out that if we come in with light and we delay, and we have to go through a beam splitter, and we delay one path relative to the other, then as we scan frequency, then if we looked in time, what would really happen is that we've got two impulses coming in here that are separated in time. And they're coincident. And we look at what happens at the output. If we do this second order correlation, then we get this modulation in frequency. And this beat period is related to the path length difference that the photons have traveled. And what's really happening is that this is really working as an interferometer, but the scattering medium is mixing the light. So you don't have to have these carefully aligned, and in fact maybe it's useful to have it misaligned, and the scattering medium is really facilitating the interaction between the photons travelling these two different paths. And so it really provides a ruler for what's happening to this light out here, but what we're interested in more fundamentally is this measurement tells us something about the light that's coming in. And it's a relatively simple measurement. So it kind of relates to the problem of information content in light. There's been some papers written in recent years about the information that can be transferred through a scattering medium with an array of sources and an array of detectors in terms of information per hertz. So it's like bits per second. And you get more information through with the scattering medium than without. So if you put vacuum there and you look at the information content, you get some information through. You put the scattering medium in, you get more through. Maybe it sounds a little bit counterintuitive, but the idea is that you're accessing more information because you have an array of sources and an array of detectors. But what this is leading to within the speckle pattern is we can think about an array of sources, an array of detectors, an array of detectors like our speckle pattern. So what we're interested in is sort of the optical analogue of what some others have looked at in the context of mobile communications in scattering media, and also multimode interference in optical fibers. So the second topic is the tomography. I want to hit a couple of highlights here. There'll be no questions, so It's either good or bad sign. So this shows a flask, and it has a black pen in it. It's not a very sophisticated measurement. In fact, we built the apparatus to make this measurement for $80 US, excluding the network analyzer that allowed us to make a coherent measurement. And this is a scattering, this is an emulsion, and it's intralipid, which is an intravenous nutrient. And basically what it is spherical fat particles with some distribution in a water or saline background. It looks like low-fat milk. Anyway, the point is that when you have it there at this sort of density, you can't see the pen through the milk. And by taking this flask with a pen in it, scanning it, fixing the source and detector, and making on one line 25 measurements, flipping them, making another 25 measurements, and modulating the light at 100 megahertz, so this gives us access to magnitude and phase, then we reconstructed this sausage-like image of the pen. And what's interesting is that we're able to get a sausage even though we had the pen is like this, and our scan plane is here. And the reason we're able to do that is because the photons scatter so much that we get information about the geometry of the pen even though we're not scanning along the axis of the pen. Anyway, so this is an iso surface for the absorption based upon the nonlinear reconstruction of a diffusion equation model for the scattering properties of the material. So the basic idea is that if we have tissue here, and let's say we're trying to find this cancer location, and we send light in, the light scatters a lot, we have an array of detectors, we measure the light of these detectors, and we try to reconstruct an image based upon a Ford model. And here the Ford model is a diffusion equation. So the parameters that we have in the diffusion equation at a single frequency are the absorption and scatter, or the absorption and the diffusion coefficient as a function of three-dimensional space. So that's the image. And we can think, and I'll show you a result where we pump at one wavelength, and if there's fluorescence, then we can measure at the fluorescing wavelength, and then we have two coupled diffusion equation models, and we can base that on the image on fluorescence. And the reason that's important is that one problem with optical imaging is to get enough contrast, have enough sensitivity. And the fluorophore enhances that sensitivity in the sense that it sucks up photons at higher energy photons and squirts them out as lower energy photons. And so we've artificially, if you like, enhanced the sensitivity. But the other thing is that we can link a targeting agent to the fluorophore. And so there are targeting agents that target cancers, not all types, but certain types of cancers. And we've been working with someone who knows about such things in chemistry. For example, some cancers express an excess of folate receptors, and one can build folate conjugates and hang a fluorophore off it, inject them, and pretty soon the fluorophore will clear out of the bloodstream except on the region where there are conjugates and the which are on the cancer cells, and the fluorophore radiates. These could also be quantum dots or something. So here's the diffusion equation. Now it's in the frequency domain. Before I showed it in the time domain, so we've taken a Fourier transform. This is the modulation frequency. So instead of measuring the impulse response in time, which we could make a measurement in a series of modulation frequencies, and we could reconstruct the temporal response. And so we're not talking about magnitude and phase measurements now at the optical wavelength. We're talking about at the modulation frequency. And here's the diffusion coefficient and the absorption coefficient, and they're the guys that constitute the image that we might care about. And we have some sort of Ford model, and X represents the image, and Y is a set of measurements. And so the idea is that from these measurements Y, we try to determine X. And that's an inverse problem. And we need to then go through some sort of optimization-based solution, because the number of unknowns is large compared to the measurement data set that we can access, and the inverse problem is ill-conditioned. And so we need to then put in some sort of regularization, and one way to look at that is in a Bayesian statistical framework where the regularization term is really the prior statistical information that we think we know about the problem. And so here's Bayes' rule for probability density functions. Here's the density function for the measurement, y given x, and here's the prior density function for x, the image. And so this is the data likelihood term, and it's a Gaussian, and here's our measurements, and here's x is the image, and f of x is the forward model, it's the diffusion equation. And so we try to adjust this model to fit x. That's the basic idea. And there's some very reasonably solid statistical framework for doing this. We spent a lot of time working on the... It's a nonlinear problem, by the way, because this function is nonlinear related to the unknowns in the diffusion equation. So I'll mention a couple of things about that. Anyway, so we have a cost function that we try to minimize, basically. And one important thing in doing that is what we found is that in a number of different problems, actually, not just this one, is that if you want to find an image, then, and you have a nonlinear problem, if you look at the cost function of the optimization surface, it doesn't have a single minimum. It can have lots of local minima. And one can get stuck in those. And another problem is that these types of inverse problems take a lot of time. So what we found was very important is to use a multi-grid solution where if we think about a three-dimensional image as being represented by D and mu sub A at a series of points, right? Then those points, let's say on a Cartesian or a rectangular grid in 3 dimensions, if we think about that representation at different grid levels, coarse, fine, finer, etc., and think about reconstructing at each of those resolutions and propagating the solutions from one to the other, then what turns out is that we can, anecdotally, we can get a better image, and we can also get it much faster. And this shows some simulations where we reconstruct. Well, this was the toy image problem, but this shows as a function of the number of iterations. If we use a fixed grid versus the multi-resolution or the multi-grid, and it's much faster. And the other thing is that here's some images. By the way, these geometries are several centimeters, and the scattering properties are like tissue. Even if you have a poor initial condition, we actually end up with a pretty good solution. This is with a very poor initial condition, and that's very important because we don't know the solution usually. So here's a fluorescence example. Here's a mouse, and room light, 785 nanometer. This is indocyanine green fluorescence, and here's the emission of 820 nanometers. So we could think about imaging based on that. And if we want to model that, then we really have then 2 diffusion equations. We have a diffusion equation at lambda x, let's call that the pump wavelength. We have a diffusion equation representing the photon scatter at the re-emission wavelength called lambda m. And the 2 are related by the fluorescence source. And this is the Fourier transform of that. And here's the lifetime of the fluorophore, and here's the quantum yield. So there's a lot of unknowns. We have this, and 2 parameters here as a function of 3D space. But if we want to solve the whole problem, then we have to make a bunch of measurements to do that. And we need to do a lambda x type measurement, a lambda m measurement, and the fluorescence measurement. But we may not need to do all that. We may know something about the solution of this problem from this one, etc. So, but we worked on all of this and solved the whole shooting match, so to speak. I'll skip. The main point I want to mention here is that we can make. If you want to get a good image, what turns out to be most important is spatial diversity, having sources and detectors at multiple spatial positions. But you can also think about temporal information or numbers of modulation frequencies. And we looked at that problem, and it turns out that spatial information is more important. You can base that on information theory. measure. The final thing I wanted to bring up is this idea of kinetic imaging, and that is if you sent something into the body, and by the way, I don't have a good answer for this, but if let's say you sent in a targeting agent that had a fluorophore, and you were able to make a bunch of measurements. By the way, it takes seconds or minutes for this targeting to occur, etc. And you were able to make measurements at a few second intervals, so you had a lot of different measurements. And you put all those measurements together, and you reconstruct some parameterized model that represents the uptake. And we looked at a toy problem. And this is a compartment model that represents the exchange between the blood plasma and the tissue and dumping out of the body or into the kidneys, liver. And one can look at a partial differential equation and come up with some parameterization like this as a function of position and time and solve for that. And what this allows, sorry about this image being so, what it allows is to differentiate these two objects based on uptake rate. And we went through, and you can put the whole thing together and solve the whole imaging problem, and this is the true phantom. You can see, sorry this is so fast, but there's some various parameters here, and if you look at the next one, you can see that that's a reconstruction that's pretty close. And why this might be important is that you might learn something about what this region of the body, the cancer cells or something, from the uptake mechanism. Now, I'm not sure exactly what, but for example, you have to be careful that the big fluorophore you're hanging off the targeting agent is not sort of messing up the transport. But from what I understand, vasculature around cancer regions is more leaky. You may also learn something about how quickly you're killing the cancer cells or something else, I'm not quite sure. It just seems to me that this mechanism of being able to image as a function of this time variable, this targeting mechanism, or some sort of transport mechanism may be important. I'm not really sure what for exactly. So what was the link, by the way, between these two? The link was sort of the diffusion model and the concept that there's a temporal impulse response. And we really looked at that as a function in two different contexts. The first one was really using it as a model for a statistical optics type set of experiments. And the second one for tomographic reconstruction. So these are some things that we're thinking about now, and in terms of something more application oriented, if you could measure something about the blood chemistry, for instance, without taking the blood out of the body, then that would be quite valuable. It's also quite difficult, but we're thinking about it again. We've been a series of collaborators, some former PhD students, and some new ones working on this problem now. And that's all. Thank you very much.
So, what is really for the advantage of your methodology compared to nuclear magnetic resonance and X-ray? The first question. The second one, can you use this on patients or only on tissue samples? Because it seems to me that the wavelength is quite dangerous for living people.
So the first question is, how does this compare with other imaging modalities? And I think so this is really the sort of second part of the talk, which is more applications oriented. And one thing that light gives you is it gives you access to spectroscopy in a frequency range that may be informative. For example, it gives you access to fluorescence, it gives you access to Raman spectroscopy, etc. The photon energies that we're talking about in the red and near infrared are not are relatively long, and so it's relatively safe. It's also possibly low cost, but I think the driving force is really what you could learn, and to a large degree I see that as complementary to ultrasound, MRI, X-ray, tomography, etc. But on the other hand, we've been working on the tomography problem for now. It was alarming the other day. I realised it's like 12 years. So if we've done all this work, and there's several other groups around the world that are working on particularly the latter part of the talk on that general area. So why isn't it in the clinic? Well, one reason is it takes a long time to get there. But another reason is maybe we really haven't solved that super important problem. So I think that's still open to question. I think
But still, can you use
Oh.
it only on some issues?
Yeah, the second part of your question was, could it be used on people? Well, we don't, and I think you have to. But I think some others have done some measurements. We've done measurements on solutions, plastic, mice, and but what we're looking at is really partial body type measurements. We're not particularly interested in the problem of taking a sample and looking at it on a slide. What we're really talking about is we're using the diffusion model, is looking at regions of tissue that are the centimeters on
But
the
it seems to
side.
me that your resolution is much lower than
Yeah. So what we're
X-ray and
right. So what's really coming out of this is that you could think about some region that's several centimeters on a side, and potentially resolution that's a millimeter or two, and that's the kind of information. So perhaps there's some sort of targeting information that may give you better resolution than that. But there's two things limiting the resolution. One is the measurement with a scattered light, but more fundamentally is the physical significance of a diffusion model, for example, or any other model that you might use.
And more specific question, also your remarks about connection between temporal and spatial information in the signal. It was not clear. I cannot understand how you can then make this kind of conclusion that you can connect them together. Since you have a diffusion and...
Yeah. Go back to... where PowerPoint helps. I can use this slide as an example. So let's say that I want to solve this equation. I want to find these parameters d and use of a as a function of 3D position, and that's my image, and at some wavelength length x. Then I have an object like this, and what I need to do is I need to have sources and detectors, right? And so I can think about having sources and detectors at different positions. And so I can take that information and reconstruct an image, and I could use a single modulation frequency, omega. And it could be 2 pi times 100 megahertz, for instance. So what's really important if I want geometrical information is to have some spatial diversity in the positions of the sources and detectors.
Do you
And
mean
so-
that you scan the laser?
Yeah, that's one way to look at it, but you could also have an optical fibre, a set of optical fibres, and you could couple them and you could switch from one to the other. Basically, you scan the laser in position, and you scan the detectors, and that could be an array of photodiodes, or it could be a CCD camera or something. But the other piece of information here is this frequency. I can go back into I can take the inverse Fourier transform of this, and this guy becomes time, right? So I could think about at each of those positions, I could make a temporal measurement. I could come in with a pulse laser, and I could use a gated CCD camera, an image intensified CCD camera, and I could at least potentially measure the temporal response at each of those positions. And I could use all of that information. Or I could Fourier transform that, and that would correspond to using a number of different frequencies. I could use 100 megahertz, 200 megahertz, 300 megahertz, etc. And I could reconstruct an image. Now, the point is, how much more do I learn about the image by using those multiple frequencies? Why do I have non-zero frequency at all? Because I have some phase information. So perhaps that relates to some geometrical information. But the question is, what we're interested in, and what I really didn't dwell on, is this trade-off between spatial diversity, where I have the sources and detectors, and temporal diversity or frequency diversity, how many frequencies I use. And we're kind of interested in that because that sort of relates to the issue of measurement design, or more fundamentally, how you really want to do this measurement. And what I said is that in general, I think that spatial diversity is more important. You might expect that, because if you want to know you have a blob there, then you better look at this blob from several different directions, perhaps, to really know it's that kind of blob.
But this isn't clear, since you are talking about frequency, right? So this is a CW laser or not? You are using CW?
No, so this, okay, let me back up. This, the optical frequency is really in this subscript. This frequency is the modulation frequency. And so if I have laser light and it's unmodulated, then its intensity doesn't vary with time. So if I look at the photodetector output, the current is not varying with time. If I modulate this intensity to 100 megahertz, I look at the photodiode current, and it has 100 megahertz information. Now, if I send that modulated light into a sample and I measure my 100 megahertz light coming out, forgetting about the DC portion of the spectrum, then I have a magnitude and a phase that I can compare with the input light. Okay, so it's the modulation frequency that appears in here. That's the modulation frequency of light. And going back to when I wrote down P of T, and I called it the temporal impulse response, or the ensemble averaged impulse response, or I call it the temporal Green's function. That P of T, using a diffusion model, is really generated by this equation in the time domain. And so that time variable corresponds to, is the Fourier transform variable associated with this omega. So this omega is not optical frequency. The optical frequency comes in here because, for example, with CW light, or pulse light if you like, I pump at one wavelength, higher energy photons, and this is the fluorescence problem, so what's coming out of the fluorophore is lower energy photons. But again, if I can also think of that measurement, I could do that measurement in time, and it's actually, this equation is linear in the sense that I can think about single frequency measurements. So I can measure this at a particular modulation frequency. So I can do the measurement either way. So my comment about spatial diversity and frequency diversity was related to where I have the sources of detectors and how many modulation frequencies I might gain from. Is that okay?
Yeah.
And by the way, it wasn't clear, but sort of, well, in the loose sense, if you stare at the problem from many different directions, then maybe you'll learn more. So those domains were several centimetres on the side, 5, 10 centimetres, and the scattering mean-free path was about a millimetre. So it's kind of like going through 10 centimetres of tissue. 10 centimetres. Give or take a little bit. The flask was actually thinner than, I think it was like 3 or 4 centimetres thick, the pen and the flask problem. But in general, that sort of tomography problem where we're looking at the fusion model, I think we're talking about many millimetres, many centimetres of tissue, and again, the measurement, the scattering problem, and the physical model, the applicability of the diffusion equation really limits the resolution.
What's your opinion on the holography? Holography with short pulses and short coherence length?
So I think holography is very beautiful. And one could think about then, if you had little scatter, that you could make a hologram of that region. The problem comes with the amount of scatter and how you can make a hologram. For example, let's say that you want to look inside the body. Now I can make a hologram of the surface. But let's say I wanted to look in 1 centimetre or 2 centimetres. I want to make a hologram of that little region or some region of the tissue in there. Then I think the problem is I can make the measurement using interference and a camera or something. But how would I de-embed the effects of the scatter so I can look inside? And there's another, so I think that's the difficulty. And there's one very popular technique called optical coherence tomography, which it's not in the everyday, not in hospitals, but it's made it to the clinic in some sense. And it uses low coherence light and an interferometer to obtain high spatial or depth information. But the length measure, getting back to the logography question, the length measure is determined assuming there's no scatter. So that's how you get the distant information. And what we're talking about with the diffusion model is that we have lots of scatter, and we're trying to parameterize that scatter using a diffusion model and obtain geometrical information, and we obtain diffusion equation parameters as a function of 3D space, let's say. Whether or not that's useful is sort of open to judgment, I think.
One more question? Okay, otherwise we thank Kevin again. Thank you.